Okay, so we've just started recording. This is a review class for the midterm, basically. There's no new material that's going to be covered, but we're just going to. I'll field questions or give examples or take examples or whatever to. Yeah, it's that kind of class. Okay. Can someone confirm that I'm sharing my OneNote screen?
Yeah, we can see it.
Perfect. Okay. Um, so let me start at the top. Can you explain what the multiple indexing schemes are from the guide? Did you mean hash-based indexing versus B plus trees? Yes. Yeah. So I'm just gonna kind of free write here, and I'll turn off my camera if that's all right, just because I don't think it's necessarily useful here. So indexing schemes. Schemes, that just means whatever, it's jargon, like how to. How do you do it? So it's a plan for indexing. Now, what is indexing in terms of database management? Indexing. This is a file that contains a data structure. It complements, I don't know, raw data on disk. Oh, another thing is it's, I'm sorry, let me do this. It's not only a file that contains a data structure, but it's a file that contains a data structure that has been, well, let's redo that. That's been designed to be stored on disk. Okay? Now, we built up to like B plus trees. I mean, like what the big points of a B plus tree, right? It's a tree. What is a tree? It's being stored on disk. How are trees stored on disk? A disk is kind of, it's an array. How do you work with trees on an array? You can be clever and have both. A tree, if you order things in a particular way and agree with yourself on some set of rules, then it's a tree stored in an array. But also, this array, why even bother with an array? It's because that's what you're limited to, storing things on hardware. Now, trees are useful because they can give guarantees about how long things will take to search or insert or what have you. And so the point of data structures for this course, there's two things. There's the general idea that data structures are useful. It's a thing that exists in the world, which is basically organizing data in a way that's useful. That's all that a data structure is. Now, there's many flavors of them because there's different ways of I don't know, wanting to benefit from the data that you have. One way is to spend some time and take up some space to create this data structure that will help you maybe search or whatever. In this case, search is the big one. Insertion, deletion, modification are also very important, but really it's search that this course is focused on. So there's this one higher level idea of what is a data structure used for, and it's just a way of organizing data for some benefit. And that if you're clever with your organization, you can leverage that to do a better job at some things you care about. The other thing is B+ trees were designed, they're one flavor of tree. I mean, there's 1,000 flavors of tree. B+ trees were developed for databases. The node size can hold so many keys that makes the tree a degree of whatever. You can fit as many keys as you can into a single node to make the degree in proportion to how much that is going to occupy on disk. And there's these types of considerations. For this, for the midterm, you don't need to know these kinds of specifics, but do know that like generally what data structures are, and a few of the specific examples that we've covered in depth in lecture, how they work. Okay, let me see. So for indexing, it's a file that stores a data structure. The data structure is useful. There's two types of data structures that we've discussed, or that we built up to, rather. A B+ tree that you don't need to know the specifics about, but just know like where it comes from, and presumably, if you were so interested, now you could look at the details of a B+ tree and understand them. But I'm not going to be asking these kinds of questions on in this course, but just trying to prepare those interested for that. Okay. And that these data structures have been developed to be stored on a disk. For a B+ tree, that includes the trade-off between how large you want a node to be, how many keys you want it to be able to store, that would also then define the degree of the tree, and also that a B+ tree has, let's see, a B+ tree versus a binary tree. Let me say this really quickly. So a binary tree is a very basic kind of tree that I started off in this lecture, or in this course, as a means to introducing what is a binary or a B+ tree. You don't need to know the specifics of a B+ tree, although I hope that you would have the knowledge to delve deeper if you so wished. A binary tree is a tree with at most 2 children. We talked about the depth of the tree being the important measure of this data structure. For a binary tree, you can have a fixed depth if it's full, or you can have a variable depth if it's not balanced. A balanced tree is one that has a fixed depth. Now, a B plus tree has a fixed depth, i.e., it's balanced. Okay, that's the B in a B plus tree. It's balanced. So the depth is controlled. And then also it has record pointers in the leaves. And has pointers to next leaf in every leaf. Okay, so every leaf has a pointer to the next leaf. This here, the pointers to the next leaf, that is the property that guarantee, or that can do range queries. Right? That's why you can do range queries so efficiently. There's a structure to the tree. You know that if you start at the root and you burrow down to a leaf, the path that you took to get there has certain guarantees. For example, when you first decided to go this direction as opposed to the other, that first choice immediately eliminated like half of the data. And every choice thereafter reduces more and more. So there's a guarantee about the number that you land at, but also that basically these things are in a ascending order, that you can, once you burrow down from the root to the leaf, that you can travel along the leaves and still have this guarantee. Here the guarantee is that things are ordered. So a range query, I want to return me the records of people who earn between $50,000 and $500,000 a year. So I have this data, I start at the root, that's the median income, and then I go down to the $50,000, the low range, and then I can travel along the bottom and return every result from 50,000 all the way up to 500,000, and then I stop. And I don't need to go from the root down to the bottom, and I don't need to do that again and again and again and again, because there's these pointers in the leaves, so that I can travel along the bottom of this tree. That's a range query, and that's what's good about a B plus tree. A B plus tree has also been designed to work well with being stored on disk. Okay, a B tree is just a balanced tree. A B plus tree is the plus is adding extra things that are good for databases, because this is going to be stored on disk, and it's taking these things into consideration. Being stored on disk is basically the size of the node. The trade-off between the depth of the tree, how broad a node is, how many keys it can hold, and whatever. Okay, so then we also talked about hash functions, and hash functions are very different than B plus trees, but they're the other option. in databases, hash-based indexes. This hasn't been necessarily designed to work for storing a data structure on disk, like a B+ tree has. A hash is a much broader category of functions. So a B tree is like a data structure that's a balanced tree, and that's a very general, but a B+ tree is a very specific, very carefully designed data structure, especially for databases. A hash-based index is like saying a B tree in the fact that it's more broad of a concept. So a hash-based index, let's see, I'll put here. A B+ tree requires ordered data that can be ordered. Right? Why is it ordered? Because that's the whole guarantee. That's the reason why it exists. I mean, you start at the root, and then now that I'm at the root, I am deciding to go left. And there's a reason why you decided to go left, because everything left is small, everything right is big, and so that's why you made that decision. This means that you need to be able to say, I'm going left because this is smaller. The concept of smaller exists, and so you take advantage of it and stuff, and fine. But there's other things that can work with yeah, fine. With things with no natural order, e.g. a smiley face, an introductory character, a number. Why not? I'll do some shapes. And whatever. Things like what in this, like, how do I order them? Or because I ordered them in this way, does that mean something? No, it doesn't. It's just, I don't know, you put them down, whatever. So this is the use of hash-based indexing. This only works with equality searches. So there's no ranges with hashes. Is this equal to that or not? That's the way that hash functions, that's the advantage of them. The advantage is I give it an input and it gives me a number, and the number is random. So the fact that it's a random number is to try to reduce collisions. Basically, what you want in a hash function is you give it an input and it returns to you something that's completely random. That's what you want it to do, is to give you something that's random. Of course, if you give it, I don't know, here's a notebook. If I give it a notebook, a physical whatever object, I give it to it, it returns to me a number. If I give it the same thing in again, it should return to me the same number. But now if I give it, I don't know, a pen, it will return to me some other different number. That's the advantage of it, that it's random like this. The disadvantage is when it's not random. So that is collisions can happen. And should be avoided. This is why it's random, because random things collide as least as possible. So you want a collision-resistant hash function, and because collisions do happen, rarely, there's a way of dealing with it. So we've talked about in lecture the way that you deal with collisions, which is that you have buckets, and this bucket, you know, you can have a pointer from one bucket to another and stuff like that. For this class, or at least for the way that I'll be giving questions to you to answer on anything that will be graded, will be higher level concepts. So be able, for example, with hash-based indexing, to describe when it's useful, which is when things can't be ordered. When you can't order things, you cannot use a B+ tree. So if you can't use a B+ tree, what else is there? A hash works. And there's this thing called collisions. They are a problem, but they can be managed in some way. That's the level of granularity I would expect an answer from you on anything that I would grade. That being said, of course, there's the details. How is it handled? How are these buckets stored on disk and all this kind of thing? But, you know, yeah, this is a class for management, not for engineering. Okay, let me see other questions here. What hardware theory do we have to know? What you need to know about hardware theory is kind of this, I guess, a B+ tree, right? So first of all, what is a tree? What's a B tree? And what is a B+ tree? A tree is a data structure where you break left or right depending on some rule. You might have many children, in which case that defines the degree of the tree and blah, blah. That's a tree. A B tree is a tree, first of all, so it matches all of those definitions. But it's also balanced. And so that's a B tree. A B+ tree is a tree that has been designed to work well with hardware. This is the extent that I want you to know about hardware. That a B+ tree, like the plus, is just doing stuff to make it useful for databases that works well on hardware. There's considerations like a block size? What's a block? What's a track? What's a sector? These are like notions on physical media. I'm not seeing my hard drive here, but you can imagine, like, I'd pick up, that hard drive that's like this, whatever, the disk with the mechanics and the spins and the motors and stuff like that. Like, I can shake it around in front of you, and that's a physical thing of hardware. Like, data is stored on that. How is that relevant? Well, there's things that you need to take into consideration, like, I don't know, the motor has to spin up, and accessing a disk is slow. Like, accessing a disk is slow. Do it infrequently, and we can have a data structure or an index to help us access the disk less frequently. The extent that I would want you to know about hardware would be to say something that's coherent about why do we want to access a hard drive infrequently? Like, a hard drive is really slow. Why is it slow? What does slow mean? Slow in what sense? This kind of thing. That's the extent that I want you to know about hardware. I went into a lot more detail as far as, like, I don't know, jargon for sizes and bits and stuff like that. But for the purposes of this course, you need to know about hardware to know that a disk is slow, memory is fast, and what does that mean? If you're saying it's fast, if you're saying it's slow, like, define fast, define slow. And I mean in a loose way here. I mean, like, slow on a disk, it's because, like, there's an actual, like, motor that's spinning up, and it's a very easy notion of slow. Like, you can hear it, like, whatever, like, the disk is slow. Memory, you don't hear. RAM, like, that's speedy. You don't need to know the details, but know that something's slow, something's fast, and be able to loosely sound like you know what you're talking about. When encoding a tree with method 2 using pointers, how do you know where to start? How do you know where is the root of the tree? Very good question. This is in reference to, let's say I'll do a very shallow tree. I'll put 3, 2, and 5. Now, how do we store this tree in the pointer method? Well, we agree that one node is going to be stored by its value, left child pointer, and right child pointer. Okay, so that's just how we're going to be storing a node. Okay, it's going to take 3 blocks. You can start at the beginning of wherever, and you read the first 3. The first value, or the first thing is going to be a value, the next thing is going to be a pointer, and then the next thing is going to be a pointer. So if we're looking at, whatever. So this is the rule that we agree on. Okay, the things are going to be stored in this way. So now if somebody gives me a block of 9 numbers, okay, it's 9 numbers. What are these numbers? Let's say it's 5, null, 3, 0, 6, 2, null. Okay, somebody gives me this list of, like, stuff. What does it mean? How is it useful? Okay, we've agreed on this rule, right? That's how we're going to be interpreting things. So now I have a list of 9 things, and I'm going to view that in chunks of 3. Okay, because that's the rule. That's the way that I'm interpreting whatever you give me. All right, so I gave it to you in the beginning. Now whatever you give me, that's the rule that I'm applying, and blah. Okay, this is the encoded version of the tree, of this picture. How do you know? Let's see. When encoding a tree with method 2 using pointers, which is what I did. That's what this is. This is encoding a tree using pointers. How do you know where to start? How do you know where is the root of the tree? So, to reinforce the point, the order does not matter with pointers. When you're encoding a tree using pointers, order doesn't matter. The fact that that chunk of 3 came before that chunk of 3, the second chunk of 3, that's an accident. No reason to read into it. Any way that there might be a way to read into it, it's an accident. But what you do need to know is the root. You have to have another pointer to the root. That's the only thing. So with a pointer method, you have chunks of 3. The particular order of how the nodes are arranged, any way you want, doesn't matter. If you want to arrange them in a particular way, you're gonna waste time. So there's no reason to. If you really wanted to, you could, but I mean, it would be wasting time to do that. So just order them however you want, and then we'll just follow the pointers. But because always with trees, you gotta start at the root. That's where you begin. You begin at the root, and then you move down the tree. So you must know where the root is. And so you can have a thing in any order, but in addition to that, you must have a pointer to the root. And given both of those things, you're in business. You can start at the root, and if you want to go left, you can follow the left pointer. If you want to, and now because of that, you can now get to the 0th element, which is here, and you could look at that child, and now you can traverse the tree. Yeah, you have to keep track of the root pointer. Okay. I'm a little confused about 4D on the study guide, so should we know when to avoid using hash-based indexing? I guess, yeah. Okay, so to be clear, B+ trees can do range queries. Hashes cannot. Okay, only B+ trees can do a range query. Return to me all of the results in between A and B. Like in that range, everything returned to me. That's what a B+ tree can do. A hash cannot do that. But a hash can work for things that have no natural order. So sometimes you're forced to use a hash-based index. There's a small point that I would not ask this kind of question, but if you're interested in some subtleties, a hash-based index, this is order 1 when collisions are rare. And a B+ tree is order log n for everything. So, if you believe your data to have very few collisions, and you only want to do equality searches, then a hash-based index could be very good for you. Because collisions, you know that they're not rare, and therefore there's this guarantee of a quote-unquote order 1 time. And because B plus trees are order log n for everything, then yes, you can do things faster using a hash-based index. But you have to know that collisions are rare, and you will never want to do a range query. In that niche case, a hash-based index is fine. In fact, preferable. But that's a niche case that I wouldn't quiz you on. Yeah, hopefully it's something that you can understand, I guess. I wanted to confirm that the record pointers from a B plus tree leaves point to the index file, and the index file buckets point to the file of records. Okay. So we have a B plus tree. I'm just gonna, I don't know, draw random stuff, B plus. And then we get down to the leaves. Remember, the leaves of a B plus tree are different than the rest. The leaves contain all record IDs. Okay, all of them are in the leaves. Some of them inevitably will appear above. But these are just record IDs and child pointers. Right, so like the top part of a B plus tree is like simplified. The leaves have extra stuff. Every single value appears in a leaf. But the things up above, that's just for navigation. So you might have some duplicates. If something appears in a leaf and it appears up above, that's like a duplicate, but that's a little bit of extra space, and who cares? The above things are for navigation. The leaves are where you end up all the time in a B plus tree. So, record pointers. Okay, now, the leaves have two extra things. One, so they have two types of pointers. One is a record pointer, and the other is a pointer to the next leaf. Okay? The record pointer is a pointer to, this is the sorry, my vocabulary is failing me. File of records. The heap file. There it is. Heap file. So this is unordered. Unordered raw data. I'm going to make it a little bit more specific. This leaf node might have multiple values. V1, V2, V3, V4, whatever. And these are going to point to the records. That's for V1, That's for V2. This is a pointer to where V3 is. And let's see. I don't know, I'll put V4 up here just for fun. Okay. Wanted to confirm the record pointers from a B plus tree leaves point to the index file. No, the index file. This is the index file. The index file is the data structure itself. So the B plus tree here is the file. If you load the index file, what you're loading is that entire data structure. And so the index file helps you navigate more quickly. It helps you find indexes. What are the indexes? The indexes are these ID numbers here, V1, V2, V3, V4. And those are the index into the corresponding records in the file of records, or the heap file. The heap file can be unordered. There might be reasons why you would want to order it. I won't go into them, but yeah. So here, the index file is either a B plus tree or it's a hash-based index. It's the parameters that define the hash function. Whatever, the index file contains itself the data structure that you're using to find what you want. So in this case, the index file is a B plus tree. The B plus tree will have indexes, maybe V2 and V1 appear here, but not V3 and V4. In the leaves, all of the records appear. In the leaves, there's, in addition, two types of pointers. That is the record pointer, right? There's 4 of them that point to the record in the file of records, and then there's a pointer to the next leaf. Apart from a disk, where can data be stored? Yeah, that's a great question. Okay, it's an abstract answer. What is data? Data, I would say, is some sequence, or at least 1 bit, because if it's not even a bit, then there's nothing to talk about. So it's at least 1 bit, maybe more. And so whatever that collection of bits are, that sequence of 1s and 0s, you call that data, or one might consider it data, because from when I start to when I end this sequence, apparently that means something to somebody, and therefore it's data to somebody. Where can that be stored? Long term, it can be stored on disk. It's a physical medium where you can, with magnets, force pieces of metal to be north or south as far as their magnetic pole. That would be long-term storage. You could also do it in memory. So, okay. In the case of a disk, that would be like magnetic poles. This is RAM. So this has, and I'm not like an electrical engineer. I don't know. I haven't pulled off this faceplate, but I happen to have some RAM. That's what it looks like. And so somehow this has something that can hold a charge. Or like, I think that they're kind of like little capacitors, basically. Like you have some array, some physical array. It might not be a straight line. It might be like a grid or I don't know what. But in any case, some of them are positive voltage and some of them are no voltage. And so you can also store data on that. And you can flip something from a 1 to a 0 very quickly on that type of medium when you're dealing with voltage, as opposed to dealing with magnetism, that's the word, on disks. There's something like this. This is a solid state drive. Again, I'm not like an electrical engineer. I don't exactly know why. I don't think it's magnets here. In fact, it's certainly not magnets. You can hold a magnet up to it and check, but it's not. It's something else, and in any case, this can hold... I think this is more like a capacitor in the fact that a capacitor, when it fills up with charge, it holds on to it until it's discharged. So this would maybe not be more of a capacitor, but maybe this is more like a capacitor. So that's a solid state drive. And then you have things like this. That is a mini SD card. That's just a reader for it. You also have cards that are just like that. That's using a different medium. You can store data on that. What can you store data on? Also a CPU. Very different hardware configuration, but certainly at particular points of time, it contains a certain amount of data. And so what can you store data on? A lot of things. Hard disks, memory, SD cards, solid state drives, arguably CPUs. There's also different levels of storage on some of the hardware that makes up a computer cache. It's called L1 cache, L2 cache. Yeah, it's a very good question. But yeah, okay. Let me read it again. Apart from a disk, where can data be stored? Lots of places. Those are some. Hard disk, solid state drive, memory, CPU, cache. That's cache, C-A-C-H-E, not C-A-S-H. Isn't 0 and 6 reversed? Oh, yes. Wait. Yes. Wait, hold on. Left child at index 0. No. Yes. Okay, I see what you're saying. Left child would be at, if that's 2, 0, 1, 2, 3, 4, 5, 6. Okay. Yeah, 3, 6, 0. Okay. This is just correcting this example. A student caught that I had swapped these two indices. So the left child is at index 6. The right child is at index 0. Very good. Okay. Sorry, but good catch. And that demonstrates that you are following along and that I can be sloppy. So great. Can you go over to 4B, indexing, be able to explain why you need to have multiple indexing schemes if you want to search through a database for different keys? Yeah, so name, age. Make it really simple. We'll have two tables. We'll have name A, B, and C with ages 10, 15, and 20. Okay, so that's our table of raw data. In fact, here, let me switch this up a little bit. CB. Okay. So here we have some raw data. The name column in no particular order. The age column in no particular order. Okay, just kind of random. That is the raw data, or the heap file, if you like. Here, to make things short, I'm just using 3 things, but I mean, it helps if you imagine this as being a gigantic long list of many, many names and many, many ages. You can do that in your mind. On the screen, I'm just doing 3 to make it simple. Now, let's say we want to find a record by name. That is different than finding a record by age. Okay? So there's 2 things that we know about. We know somebody's name, and if you give me a name, can I return to you that entire row that corresponds to that name? Or there's another choice where you give me an age. I look to see if there's 1 or many people that have that age, and I return the record of people with that age. Okay? There's only 2 properties that we can search for, or that we can return records based off of, and that's, in this case, name and age. And one thing that I am stating, hopefully you would have enough understanding to kind of work this out for yourself, but otherwise just understand that it's true. You can make a data structure to find records efficiently based on some property. There's 2 properties here, name and age. I can construct a data structure that will very efficiently find a record by name. Okay, maybe I'll make a B+ tree for name. So the B+ tree, based on the name, I'll start at the root. If the name is alphabetically before the root, I'll go one way. If it's alphabetically after, I'll go another way, or alphabetically in between a range, I'll go somewhere in between, whatever. I can make a B+ tree. You give me a name, I can start at the root, and I can burrow my way down to a leaf in log n steps to find a name that matches what you're looking for. Now, can I use that same tree, that same data structure, to find somebody by their age? And the answer is no, you can't do that. Instead, if you want to find somebody efficiently by their age, you must construct a new B+ tree for age. Okay, you need 2 different data structures. You might know enough now to be able to make, to prove that this is the case. Otherwise, just know that it's the case. You cannot have a data structure that you can navigate efficiently based on 2 different criteria. You have to tailor make a data structure for one specific thing. In this case, I can make one data structure to find records by name efficiently, and I can make another data structure to find records based on age efficiently. I can't do both. If you want to find records by more than one criteria, You must have multiple different data structures to do that. Okay. Hold on, let me see if I missed questions. For a hash function, it returns a pseudo-random number that is an index for the index file. And then that points to the file of records. Really good question. Yeah, like I like this. Yeah, you're being very detailed. That's good. So an index file, this is a data structure. Okay, stored, I'll write it out, stored in a file. Okay, that's all that an index file is. An index file is a data structure. It can be an encoded B+ tree, and there's probably more details behind how exactly it's saved in file that I'm not covering in this class, but that's fine, so long you get the basic idea that, I mean, it's a data structure, it's going to be a file, it's some sequence of numbers that are interpreted in a particular way that is useful for this thing, and, you know. So that's what an index file is. An index file is a data structure. For DBMS, in particular the databases that we're talking about, which are relational, SQL being the most popular of them. This could be a B+ tree, or this could be a hash-based index. And the hash-based index here, that would be a very complicated way of being stored on file. You might be able to open up a B+ tree or an index file that's a B+ tree and actually read it, like with your eyes, and kind of figure out what it's doing. For a hash-based index, not so much. The hash-based index, this is going to be a function that maps numbers. It takes some input and it outputs a number. And that's going to be some function. And the way that you write that function, in particular the sequence of ones and zeros and stuff, of how that would look on disk, is who knows. I mean, like, that's a very, very low level kind of thing. And you don't need to understand that. But it's a function that's stored in the file. So if you load a hash-based index, you're just loading a hash function. And then if you want to use it, now you have the function, and you can give it an input, and it'll return back to you a number. So that's an index file, or an index. So for a hash function, it returns a pseudorandom number that is an index. No, when I'm saying index, I'm talking about an index file. And the index file, again, is the data structure that you use to find things on the file of records, or the heap file. A little bit more about the hash. So this is going, okay, so there's a file on disk. It's the index file. Maybe I'm using hash-based indexing. So I load this file, I open the file, okay? Now I have a function. That's a hash function. Okay, so there was the index file that was on disk. I load up the file, and I now have a function that I can give stuff to, and it will return to me back a number. the number, so let's say I don't know, I'll stick with this. Load this. Get back a hash function. Okay. Now, let's say that I take this function f and I give it a smiley face. And this returns back to me the number 4268900, whatever. Some number, some random number. What does this number mean? So there's the index file. This would be the hash function. There's, I'll call it the bucket 0 file, and then the extra buckets file. So there's one file that I load, I get back the hash function. Now, I load the hash function, I give it a smiley face, and I get back this number. That is the number for bucket 0, which means that means that in this file, there's lots of lines, 0, 0, 0, and I don't know, this is 9, 9, 9. Here is 4268900. Okay. That's the row number. So that's what this returns back to you. It returns back to you a random number. You interpret that random number as the line in another file. Hopefully, the record for the smiley face is there. Maybe it's not. There's, X is this one that's at position Y. And then here is a pointer. I'll call that the number 32. Maybe the smiley face is here. And then this would be a pointer to the heap file. We'll use some different colors here. So that points to X, this points to Y. And that's at position Y. No. Oh. And I don't know, now that points to Z. It's a different record. Okay. So this is how a hash function works, right? In the index file, you have the hash function itself. That returns back to you some random number that corresponds to, let's say, a row in another file. hopefully the record that you're looking for exists in the very first file. If that's the case, then you can find, for example, if you're looking for that record, you can find it in one go. So you use your hash function, you land in this first file, and then in one go, that row contains the pointer to the record that you care about in the heap file. That's the order 1 case when the hash function works most efficiently. But because of collisions, maybe this number, that row number appears too many times. And now this row got filled up. I'm looking for the smiley face. It's not in this file, so now I have to go and load up another file. And okay, now that file has the pointer to the record that I care about. So a hash function does return a pseudo-random number. This pseudo-random number that the hash function returns is the number of a location to look first. Like, for example, a row. That's where you look first for the record that you're looking for. If it's not there, then this file will have another pointer that will go to another file, and then you can look in that file and that row for that record. If that one gets filled up, then it might go to another file, and on and on. It depends on how many collisions you have. Hopefully they're few. Most of the time they're very few. You don't have to go very deep. 1 or 2 files is fine. Okay. Could you give an example of a hard ER diagram that would come on the exam and solve it, please? Ooh, we have 8 minutes left. Let me see if I can come up with something. Actually, to save me a little bit of time, I can try to come up with something, but is there an example of an ER diagram that a student considers hard that you would like me to try to go through, how to make that into tables? Something you came up with yourself, or that you came up somewhere else and you're stuck on? Anything like that? Oh, okay. Then so let's work with 3 entities, 1 weak entity, just to throw it in there. Again, the weak entity, so here, hold on, first of all, here we have 3 entities, 1, 2, 3, those are the rectangles. And then we have 2 relationships, those are the diamonds. And these signify a weak entity because it's in bold, and for reasons of this notation, the relationship is similarly in bold. Let's say that has some key value A. This has some key value alpha. This has a key value 1. Remember, because it's a weak entity, it doesn't have a proper kind of primary key. And whatever. Call this A, call this G, call this N. I mean, I don't know. I don't know what's a hard one, you know? Make that exactly one. Just kind of making stuff up, I guess, like this. You know what? Actually, I do have a hard one that I'll just give it to a preview, or as a preview to you, because it's an extra credit. I'll give it as an extra credit problem. But it's a good thing to know about. Here, the keys don't matter as much. But this, that's a valid ER diagram. A has to have at least one B, and B has to have at least one A. Right? A has to have at least one B. B has to have at least one A. Fine. Nothing wrong with this ER diagram. But this you cannot make into tables. This ER diagram, there's no way to capture this using tables. That's a good thing to know. Strictly speaking, ER diagrams are more broad than the relational model. Where the relational model, I mean, like that's tables, you know. That is a relation, which is the same thing as a table. There's no way to do it. Can't do it. You can play around with this. This is not something that I would ask for a measure of your knowledge. But yeah, this is a really good extra credit problem, and now maybe you can think about it a little bit. Why? Why can't you do this? Try and fail. I mean, certainly you'll have to try. I guarantee you that you'll fail. And then try to figure out why. Why doesn't this work? That one's harder. But let's see. Here we'd have a table A. I'll leave that kind of in the periphery for you. And by the way, we're coming up on 3. If you want to get off, that's fine. A, B. Let's see, we'd have R1. So I usually start off with the entities because I always know that they're going to be tables. There's alpha, beta. What is that N? Table N has, what is it? Oh, the number 1. Okay, and now this is going to be a compound key with G. So there will have to be an alpha here. And this is not null. Okay, so let's see. So what I'm doing here is going through this ER diagram. I start off with the entities. Right? So there's A. We have column A, column B. A is keyed. We have G, columns alpha, beta. Alpha is keyed. And now we come to table N, which is the last entity. So that has a key 1, but because it's a weak entity, that means it relies on something else. And so here that's the alpha, right? So N relies on G. Erase some of these. A, B, okay. So here, because this is a weak entity and it relies on that entity, then the key 1 has to be paired with this key alpha. That key alpha cannot be null because it's a weak entity, n. And let's see here. G has exactly one A. Oh, sorry, forgot one more thing. The foreign keys. This alpha is a foreign key here and on delete cascade. So if the corresponding alpha gets deleted, so should the corresponding entity in N. Let's see about these relationships. G has to have exactly one A. So that's going to require another column here, A. And exactly one A. One A, yeah, that could be more than one, so I don't need to key this. I do not need to key it because, for example, I could have two values here have the same A. Yeah, these being the same is no problem. It's just that every G here needs some A. So I'm going to add that as a column. I'm not requiring that those are different, so I'll leave that unkeyed. A can have 0 or many G's. Hold on, so that A is also a foreign key here. N has to have at least one G. So for the same reasons, that is going to require an alpha that is not keyed. At least one. No, sorry. If that's at least one. Okay, so then R2 is going to have an alpha and a 1. Every of these need at least 1. So, okay, it'll be keyed like that. R2, here we can have at most 1. And then we can have repeats because that's not keyed. So, oh, and that's not null. Not null. And because it's not keyed, you can have more than 1 because it can appear more than once. Yeah, it's not going to violate anything. So that's that captures R2. And for R1, I think it's just GR1. A can have many G's. And A can have many G's. Yeah, like that. What is on delete cascade? What that means is, let's say, I don't know, this is Amy. It's the number 32 and the number 0, whatever. And here, there's also the name Amy that has a smiley face, whatever. Okay? The on delete cascade means here in this table, Amy, gonna get rid of her. Okay? Amy is the primary key. So I'm going to delete that row. Amy, she's gone. On delete cascade means that Amy here is a foreign key into this table. And because Amy is gone, everything about Amy has to be gone. So not only am I going to delete Amy here, but I'm going to cascade it. It's like falling dominoes, right? I knock down Amy in this table, and here, Amy has something to do with her in that table, gone. I'm gonna delete Amy from this table, and then I'm going to cascade. I'm going to continue that process of deleting for anything that connects to it. And by things that connect, I mean any foreign keys. So you would follow this foreign key back, and then because that foreign key corresponds to something that we deleted, we delete the entry in this table as well. Is the A foreign key from table A into table G? The arrow in your diagram points the other way around. Hold on, let me delete some of these. No, right. So this question is this key, A. That's the original key. That's coming from this table. That is not a foreign key. That's the key that defines entries in table A. Little a defines entries in table big A. This A here in this table is referring to the A's that appear in this one. So that's why it's a foreign key that is pointing in this direction. The exam is due on Friday night, correct. Friday night, 11:59. Okay, well, we are like 10 minutes past, guys. I don't know who else is here, or if there's any other questions or anything. Okay. What time are you posting today? Here in the next hour or two. I'll try to be earlier about it. Which is the arrow pointing for the alpha key from G to N? For the alpha key. Oh, that is pointing this way. Here. Again, for the same reason. Here, alpha is what uniquely identifies G. So that's how you find unique entries in G is via key alpha. Now here in table N, any alpha that you see here, that's coming from the alpha in G, which is why the arrow points from table N to table G. That being said, I mean, you point it the other way around, I don't care. Just be consistent, okay? Like, yeah, if you change your mind with which way you're pointing the arrow, I'm totally lost. If you point the arrow, just be consistent. It doesn't matter, yeah. That's the reason why I'm making these arrows like that, yeah. Okay. Okay, excellent. Let me stop this recording.